Exactly. It sounds, well, pretty wild, but that's exactly what we're diving into today, the light-matter interchange.
Mm. It does have that sci-fi ring to it, doesn't it?
Yeah.
But we're basing this on a really comprehensive report. It's titled The Light Matter Interchange: Creation, Annihilation, and Cosmic Imbalance.
Yeah, and this report it really gets into how these fundamental transformations happen, how they bridge what seems like this, huge gap between light and matter.
It really does. It unpacks the whole thing.
So our mission here really is to pull out the key insights from this material. We'll touch on foundational stuff like, Einstein's famous equation, EMC.
Right, but also the really cutting-edge things, like the experiments happening in particle accelerators.
And those big cosmic mysteries, like what happened in the early universe. We want to help you really grasp how energy can, well, materialize and then dematerialize.
Uncover the implications, basically,
Yeah.
which are pretty profound.
Yeah, offer you a shortcut to getting up to speed, maybe with a few of those aha moments along the way. So let's get into this cosmic dance.
Okay, so one thing the report points out right away is that this vast gulf we imagine between light and matter, it's not really a gulf, it's more like a bridge built by
The
physics.
bridge, I like that.
Yeah. And at its heart, the transformation is just energy switching states,
Mm.
from one form to another.
And it's all tightly controlled, right? By the rules of quantum mechanics and relativity.
Exactly. Meticulously governed, as the report puts it.
Which, I mean, that can mess with our everyday intuition, can't it? Because we usually think of light as, well, a wave, just spreading out.
Right. But the report quickly gets into its quantum side. Light is made of these little packets of energy, photons.
Photons, okay. And they're elementary particles.
Yep. Elementary particles. Specifically, they're bosons, the fourth carriers. And the key things are zero rest mass, no electric charge.
And they just, what, zip around at the speed of light?
Always. That's their thing.
This wave-particle duality, it seems, central.
Oh, absolutely critical. You need both ways of thinking about it. Einstein's work, the photoelectric effect, showed light delivers energy in these quantized chunks, the photons.
So the energy depends on the frequency. Higher frequency, more energetic photon.
Precisely. So light travels like a wave, but when it hits something, it acts like a particle. And photons cover the whole electromagnetic spectrum, right?
Yeah.
Radio waves, gamma rays. It's all photons, just with different energies.
Okay, so that's light. Then there's matter, and that's made of different particles.
Right. Matter's built from fermions. Think quarks, electrons, that kind of stuff, the building blocks.
And the big difference is mass.
The big difference is rest mass. Fermions have it, photons don't. It's an intrinsic property, meaning they fundamentally can't travel at the speed of light.
Okay, but the report mentions something interesting about mass. It's not just adding up the parts.
Ah, yeah, that's a fantastic point it makes. Take a proton. It's made of 3 quarks. But the proton's mass is way, way more than just the sum of those 3 quarks' rest masses.
So where does the extra mass come from?
Most of it is actually energy. It's the kinetic energy of the quarks whizzing around inside, and crucially, the binding energy from the strong nuclear force holding them together.
Wow. So Equivalence is playing out right there, inside a proton.
Absolutely. It's a real-world example happening constantly at the subatomic level. Mass is energy.
So Equivalence really ties it all together then. It's not just saying you can convert mass to energy, it's saying they are kind of the same thing.
Exactly. It's a statement of identity, not just conversion. Your hand, this chair, the earth, it's all, in a very deep sense, just frozen or congealed energy.
That's the real mind bender. The universe is just energy constantly changing shape.
That's a great way to put it. And the report clarifies the full picture uses the relativistic energy-momentum relation. That's the equation that covers both light and matter.
How so?
Well, it shows that a massless photon and a massive electron are just different solutions within the same energy framework. When light becomes matter, you're basically converting massless, moving energy into particles that now have rest energy, or mass.
So it's just shifting energy from one column to another in the universe's ledger book while keeping the total balanced?
Precisely. It's a transition, but the fundamental conservation laws, energy and momentum, hold firm.
Okay. So if matter is just congealed energy, how does light actually do that? How does it become matter? What's the mechanism?
Right, the process. The most direct way is something called pair production.
Pair production.
Yeah. Pure energy light spontaneously materializes into a particle and its antimatter twin. The classic example everyone uses is a high-energy photon, a gamma ray, turning into an electron and a positron.
A positron. That's the antimatter electron, right?
That's the one. Looks just like an electron, but with a positive charge.
And there are rules for this. It doesn't just happen with any old light.
No, definitely not. There's a strict energy requirement. For an electron-positron pair, the photon needs at least 1.022 mega-electron volts, MeV, of energy.
1.022 MeV. Why that specific number?
Because that's exactly the combined rest mass energy of one electron and one positron, according to Yves CFT-Montry. You need enough energy to create their mass.
And if the photon has more energy than that?
The extra energy just becomes kinetic energy. It makes the new electron and positron fly apart faster.
Okay, but wait, you said a lone photon. Why can't it just do this on its own in empty space if it has enough energy?
Good question. That gets into the conservation laws again. A lone photon transforming in a vacuum would actually violate the conservation of both energy and momentum at the same time.
How?
It's tricky, but basically you can't find a reference frame where both are conserved simultaneously if it's just the photon decaying into two massive particles. It's a kinematic no-go. The universe says nope.
So, if a single photon can't do it alone, how does pair production actually happen then? What's missing?
It needs help. It needs a third party, usually a heavy atomic nucleus nearby.
A nucleus, like
Yeah.
from an atom, what does that do?
It acts like a momentum anchor, maybe a catalyst. When the photon interacts near the nucleus recoils slightly. It absorbs just the right amount of momentum, but hardly any energy, because it's so heavy to make the whole interaction balance.
So the nucleus takes the momentum hit, allowing the energy to convert into mass while keeping the universe's books balanced.
Exactly. Total momentum before photon equals total momentum after electron plus positron plus recoiling nucleus. It shows energy can't just become mass willy-nilly. It needs a specific mediated interaction that respects these fundamental symmetries.
So it needs a dance partner or maybe, like you said, a momentum anchor.
Yeah.
But what if you have two photons? Can they do it without the nucleus?
Yes. Excellent point. That leads to the Bright-Wheeler process.
Great.
Yeah. Two photons collide, and bam, they create a particle-antiparticle pair directly. Electron and positron, for instance.
And no nucleus needed this time.
Nope. Because now you have two initial particles, the two photons. Their combined momentum can be set up before the collision so that the momentum of the resulting electron and positron perfectly balances out. Conservation laws are satisfied without needing that third body.
So light literally colliding with light to make matter?
Exactly. It's a really pure manifestation of Imsuvasquite. It happens out in space, in extreme environments, and scientists are actually trying hard to make it happen in labs right now.
Wow. Okay, so light becomes matter via pair production. What about the reverse? Can matter go back to being light?
Absolutely. That process is called annihilation.
Annihilation sounds dramatic.
It is. It's the mirror image of pair production. Conversion of mass back into energy, usually photons.
And it follows the same rules. Conservation laws.
Rigorously. Energy, momentum, electric charge, spin, all conserved. When a particle meets its antiparticle counterpart, they wipe each other out. Their combined mass, plus any kinetic energy they had, gets converted into other particles, most often photons.
So let's take the simple case. An electron meets a positron. What happens?
If they meet at low energy, basically when they're almost stationary, they annihilate and produce two gamma-ray photons.
Two photons, why not just one?
Momentum again. If they're nearly at rest initially, the total momentum is basically zero. If only one photon came out, it would fly off with momentum, violating conservation. You need two photons shooting off in perfectly opposite directions so their momentum cancel out, keeping the total momentum zero.
Makes sense. And the energy of these photons?
Each one carries exactly 0.511 MeV, exactly the rest mass energy of a single electron or positron. So the total energy released equals the total rest mass that was destroyed, and finding that specific 0.511 MeV gamma ray signature is a dead giveaway that positron annihilation is happening somewhere.
That's incredibly neat and precise. What about bigger particles, like a proton and an antiproton? Do they just make two photons too?
No, that's much messier. An electron is fundamental, it's simple. A proton isn't.
It's made of quarks.
Exactly. A proton is a composite particle. So when a proton and an antiproton collide, it's really a quark from the proton meeting an antiquark from the antiproton. They annihilate, sure, often creating a gluon initially.
A gluon, one of the strong force particles.
That's right. But then there's all this leftover energy, and the other quarks and antiquarks are still there. This triggers a whole cascade called hadronization.
Hadronization.
Yeah, the energy in remaining quarks basically condense into a whole bunch of new, mostly unstable composite particles, other hadrons like pions. So instead of two clean photons, you get this spray, this jet of many different particles shooting out. It's complex, but incredibly energetic.
It's just amazing that these processes, pair production and annihilation, aren't just equations on a blackboard. The report really drives home that we see this happening everywhere.
Oh yeah, across incredible scales. From inside labs to the furthest reaches of the cosmos, the same fundamental rules apply.
So in the lab, how do we actually see this?
Well, the most famous examples are particle accelerators, like the Large Hadron Collider, the LHC, at CERN.
Right, smashing protons together at nearly the speed of light.
Exactly. You pump particles full of kinetic energy, smash them together, and that kinetic energy converts back into mass via MC-Crissa, again creating showers of new particles, including heavy particle-antiparticle pairs that wouldn't normally exist.
And studying those particles tells us about the fundamental laws.
Precisely. We make incredibly precise measurements, testing the standard model of particle physics to its limits, looking for tiny deviations.
And don't we also have places specifically designed to make antimatter?
We do. Places like CERN's antiproton decelerator complex. They're basically antimatter factories.
Seriously? Factories?
Well, yeah. They produce antiprotons, slow them way down, and trap them. They've even combined antiprotons with positrons to make actual antihydrogen atoms.
Wow, and trap them. For how long?
They've held on to antihydrogen for over 16 minutes now, which is long enough to start doing really precise experiments, comparing its properties directly to regular hydrogen, looking for any tiny difference.
That sounds like something straight out of Star Trek.
It kind of does, but it's real experimental physics happening today. And there's another way, too, using lasers.
Lasers making matter.
Sort of. You use incredibly powerful, intense lasers, fire them at a target. This accelerates electrons in the target like crazy. These electrons then interact with the intense laser field or with nuclei and produce high-energy photons.
Okay, so the laser makes photons.
Right, gamma rays. And then those photons, within that same extreme environment, undergo pair production. They turn into electron-positron pairs. They've managed to create billions of positrons in a single laser shot this way.
Billions from light.
Billions. It's literally creating matter-antimatter pairs from light energy in the lab, a relatively new and exciting frontier.
Okay, so labs are one thing, but you mentioned cosmic scales too. Where does nature do this?
Oh, nature's laboratories are far more extreme. Think about the very beginning, the Big Bang.
Right after the explosion.
In those first fractions of a second, the universe was unbelievably hot and dense, just a searing soup of pure energy. Photons had enormous energies.
Enough energy to do pair production.
Easily. Enough to create pairs of all kinds of particles and antiparticles, electrons, positrons, quarks, antiquarks, everything. For a short time, pair production and annihilation were happening constantly in equilibrium.
A constant churning back and forth between matter and energy.
Exactly. Matter popping into existence, then annihilating back into photons, then popping out again. But as the universe expanded, it cooled down.
So the average energy of the photons dropped.
Right. Eventually, photons didn't have enough energy anymore to create pairs of the heavier particles. Then later, not enough for lighter ones like electrons and positrons, pair production stopped or froze out for each particle type.
And the annihilations continued for a bit longer.
Until most particles found an antiparticle. But if there was a slight imbalance,
Yeah.
we'll get to that. But this freeze-out basically locked in the raw material composition of the universe we see today.
It's not just the ancient past, though, is it? What about things happening now?
Oh yeah. Gamma-ray bursts, for instance. GRBs. They're the most powerful electromagnetic explosions we know of in the universe.
And they involve pair production.
The leading theories suggest they do, yeah. In the incredibly energetic jets of plasma shooting out from, say, a collapsing massive star or merging neutron stars, conditions are extreme. High-energy photons created in these jets likely convert into electron-positron pairs.
Creating a kind of cascade.
Exactly. An electromagnetic cascade, a plasma of electrons, positrons, and photons, which is thought to be responsible for the intense gamma rays we detect billions of light years away.
Wow. And even closer to home, like cosmic rays hitting our atmosphere.
Yep, happens all the time above our heads.
Yeah.
High-energy particles from space cosmic rays slam into air molecules. This creates a shower of secondary particles.
Like
Pions are common. Some of those are neutral pions, which decay almost instantly into two high-energy gamma rays.
and those gamma rays.
If they pass close to an atmospheric nucleus, they can undergo pair production, creating more electrons and positrons, contributing to the cascade, the extensive air shower that rains down particles to the ground. It's like tiny particle physics experiments happening naturally overhead constantly.
So all this evidence, lab and cosmic, it points to some pretty deep implications, doesn't it? And maybe the biggest one is this mystery about matter and antimatter.
Yes, the matter-antimatter asymmetry problem. It's one of the biggest puzzles in physics.
Because pair production seems perfectly symmetrical, right? You always get one particle and one antiparticle.
Exactly. So based on what we know about pair production in the early universe, the Big Bang should have created precisely equal amounts of matter and antimatter.
But if that happened, what then?
Well, as the universe cooled, every single particle should have eventually found an antiparticle partner. They would have all annihilated each other.
Leaving behind.
A universe filled pretty much only with light, photons, maybe some neutrinos, but certainly no protons, no neutrons, no electrons to make atoms, stars, galaxies, or us.
But clearly that's not what happened. We are here. The universe is overwhelmingly made of matter.
Which means there must have been a tiny, tiny imbalance right from the start. The estimates are something like, for every billion particle-antiparticle pairs, there was just one extra particle of matter left over.
1 in a billion. That's it.
That tiny leftover fraction is what survived the annihilation phase to become everything we see. It's an incredibly small asymmetry, but cosmically crucial.
So what caused that asymmetry? Does the standard model explain it?
It implies there must be some subtle difference in the laws of physics for matter versus antimatter, a violation of what's called charge parity or CP symmetry.
And have we seen CP violation?
We have, yes, experimentally observed in the behavior of some particles, like quarks. But the problem is, the amount of CP violation predicted by the standard model is far, far too small.
Not enough to explain that 1 in a billion leftover matter.
Not by a long shot. Orders of magnitude too small. And that discrepancy is one of the most compelling reasons we think there must be physics beyond the standard model. New particles, new forces, something we haven't discovered yet.
So studying annihilation precisely is actually a way to hunt for this new physics.
Absolutely. It turns annihilation studies, especially with antimatter traps, into a high-precision search for clues about why we exist.
Wow. Okay, beyond the cosmic mystery, does pair production tell us anything else? Like about empty space itself?
It does, yeah. It relates to the quantum vacuum. Turns out, empty space isn't really empty.
Not empty. What's in it?
According to quantum field theory, it's a seething soup of virtual particles. Particle-antiparticle pairs that constantly flicker into and out of existence, borrowing energy for incredibly short times allowed by the uncertainty principle.
Virtual particles, so not quite real.
Not usually directly observable, no, but an energetic photon passing through this vacuum can be thought of as hitting one of these virtual pairs and giving it enough energy to become real, to promote it into observable, lasting particles.
So pair production isn't creating from nothing. It's more like activating something that was already latent in the vacuum.
That's one way to look at it, yeah. Exciting a particle out of this sea of virtual states into the real world. This whole idea of the active vacuum is pretty wild. And it even comes up in theories about things like Hawking radiation from black holes.
Mind-bending stuff. Is there a more down-to-earth application of all this?
Oh, definitely.
Yeah.
A really important one, actually, that many people might have encountered, PET scans in medicine.
PET scans. Positron emission tomography. How does that relate?
It uses annihilation directly. In a PET scan, the patient is given a special tracer molecule tagged with a radioactive isotope that decays by emitting positrons.
Antimatter inside the body.
Yep, tiny amounts. Each positron travels just a short distance, maybe a few millimeters, before it bumps into an electron in the surrounding tissue.
And then annihilation.
Exactly. Electron meets positron, they annihilate, producing those two characteristic 0.511 memavate gamma rays flying off in opposite direction.
Ah, the signature we talked about.
Right. Detectors arranged around the patient pick up these pairs of back-to-back photons. By tracking where these pairs come from, a computer can reconstruct a 3D map showing exactly where the traits are concentrated in the body.
Which tells doctors.
It usually maps metabolic activity.
Mm-hmm.
Cancer cells, for example, are often more metabolically active and take up more tracer, so they light up on a PET scan. It's invaluable for diagnosing cancer, but also heart problems, brain disorders, all thanks to matter-antimatter annihilation.
So clearly this whole field light-matter interchange, it's not just history. It's still very active.
Oh, absolutely. Very much an ongoing area of research. Like I mentioned, people are building these new, super powerful laser facilities.
To try and see the Bright-Wheeler process. Light hitting light to make matter?
That's a major goal, yes. To observe it directly and controllably in the lab for the first time would be a huge confirmation and could open up new study areas.
And the antimatter research.
That continues full steam ahead, too.
Yeah.
At CERN and elsewhere, they're constantly refining techniques to make and trap more antimatter. and to measure its properties with ever-increasing precision. Still hunting for that tiny difference compared to matter that could explain the cosmic asymmetry, looking for that new physics.
Okay, so let's try to wrap this up. We've journeyed through this pretty amazing realm, haven't we? Where light and matter are revealed as, well, fundamentally interchangeable, just different forms of energy.
Yeah, from the sort of quantum dance between photons and fermions to the really dramatic processes, pair production light becoming matter, and annihilation matter dissolving back into pure energy.
And it's all governed by strict rules, conservation laws, especially that core energy momentum relationship.
And we've seen this isn't just theory, it's proven, verified experimentally across just an astonishing range of conditions.
Right, from the controlled collisions in machines like the LHC,
And those antimatter factories making positrons with lasers.
all the way back to the Big Bang's fiery start and out to exploding stars' gamma ray bursts.
The same fundamental laws are precisely at work everywhere, shaping reality.
But that success, that beautiful symmetry we see in the laws, actually highlights one of the biggest remaining questions in science.
The matter-antimatter asymmetry problem, yeah.
Yeah.
Despite the symmetry in how light and matter convert, the universe we live in is just overwhelmingly matter.
Our existence literally points to some tiny, still unexplained hiccup in the early universe. Just that one extra matter particle for every billion pairs.
And that transforms this whole area. It's not a closed book. Studying pair production and annihilation precisely becomes a vital, ongoing search.
Pushing the boundaries with experiments, right?
Yeah.
Trying to catch light turning into matter directly with Brightwheeler.
And scrutinizing antimatter at places like CERN, searching tirelessly for those subtle clues, those deviations from the standard model that might finally crack the code of a matter-filled universe.
So maybe as you look around at the solid world, your chair, your hand, just consider this. It's all fundamentally just congealed light.
Existing because of incredibly precise physical laws, but also because of some still mysterious rule-breaking that allowed us to survive.
Makes you wonder, doesn't it? What tiny crack in our current understanding, what subtle effect we haven't measured yet, holds the key to that ultimate cosmic secret.